Greetings! We
are the Earth
Saving
Club ESC!
In this video, we will talk about the destiny of war's coral reefs via supreme structure of feedback loop.
Yay!
To begin our negative feedback loop, I want to focus on the highly energy-intensive sector. Think of space exploration, bulk shipping, and aerospace. In our model, these are the inflow. As these industries expand, they increase the total heat energy inflow, which is our stock. What matters here is that carbon-intensive energy use is transformed into accumulated heat in the Earth system. In other words, carbon first appears through fossil fuel-based energy consumption, but in this part of the loop, what we actually track is its conversion into heat. That it circulates through the atmosphere, raising our global temperature. That accumulated heat then moves to other bodies like water temperature, which is our outflow. And once ocean temperature rises, coral reefs face stronger thermal stress, more frequent bleaching, and lower resilience overall.
While that sector contributes heat to the ocean, there is another sector that influences water carbon rates. China's Hainan Underwater Data Center directly discharges CO2 into surrounding seawater during the server cooling process. That's our inflow. This gradually raises acidification rates, which is our stock. The outflow is increasing carbon density in the water, which strips away the carbonate ion corals needs to build their skeletons. NOAA Coral Reef Watch confirms that the South China Sea, where this UDC operates, already sits among the highest heat stress zones for coral globally. So this additional chemical pressure doesn't just add to the problem, it accelerates it.
Both water temperature from TED sector and carbon density in Dongmi sector directly affect coral reef populations as an inflow, since they are crucial environmental variables when it comes to their survival. Take the Mauritius coral reef, for example. Located on the southern coast of East Africa, Madagascar, it provides a stable and warm temperature and moderate carbon density to a healthy low to moderate density. It's a good place for corals reefs to form. As carbon enters water, more acidic water is introduced, generating higher carbonate ions, which corals rely for their skeletal growth. More acidification means corals will be weaker and slower to grow fully. Not only that, but as temperature increases in the water, especially notable in 1998 and 2016 heat spikes, for our case example, the corals are not equipped to survive such a harsh temperature. These factors outflow to the entire coral reefs population.
The damage does not stop at the coral itself. When coral reef biodiversity declines, it triggers a cascading stalk of disruption that ripples outward into the entire marine ecosystem, functioning as a self-reinforcing negative carbon loop. Coral reefs cover less than 1% of the ocean floor, yet support an estimated 25% of all known marine species, making them a critical natural resource infrastructure. Coral structures provide nursery grounds for juvenile fish, stabilize coastal sediment, and regulate local nutrient cycles. When thermal stress and acidification weaken coral skeletons, this entire service architecture begins to collapse. When coral population declines, the entire marine ecosystem disruption accumulates. The outflow from this stock is the entire marine biosphere, including the food, culture, and environmental stability we rely on.
Currently, activities such as marine culture, agriculture, and tourism directly influences the system's inflow of our marine system, continuously influencing the stock of socio-economic status. However, when faced with the entire feedback of coral reefs collapse to eventual marine life disruption, vague call to action happens as an outflow, more than less. Blue economy, for example, a technical finance system that is critic to be lacking specific, actionable methods, is an example of our appeal to vector technology. This additionally fits with public opinion, where we have fear control mechanism that reduce rational decision-making and triggers crowd effects to postpone and stay ignorant. These attitudes once again feed back into opportunities, into carbon production and heat increase, raising the cycle up to another level. To overcome these cognitive limitations and shift the system into a healthy, positive feedback loop, education and awareness building models can be one leverage point to play a central role. Going beyond simple knowledge transfer or fear mongering. We need to provide specific methodological guidelines in connection with civic eco-protection groups, thereby boosting the public's response efficacy so they feel capable of mitigating the threat. When organizational efforts such as green bonds, international regulations, and subsidies are firmly integrated in a cross-sectional manner, people can finally move past fear and enact genuine behavior change.
Simon showed how education shifts behavior, but individual action cannot restructure global systems alone. That requires international regulation as another leverage point, specifically the financial mechanisms that convert policy into ground level change. Green bonds and eco funds direct capital toward coral restoration, ocean monitoring, and carbon capture infrastructure with financial incentives. Methods like subsidies for low-emission coastal industries and compensation frameworks for minority communities disproportionately impacted by reef collapse can reduce economic incentives to exploit degrading ecosystems. These financial tools elevate the organizational level effort, aligning governments, NGOs, and private actors around funded shared targets.
Let's take a look at the technology leverage point. We realize that preserving coral itself is not enough. We need to consistently build a future where the world temperature can be moderated, which means capturing carbon dioxide that raises temperature and acidification in the first place. The first solution is adapting to the situation and directly influencing coral populations. Going back to the Mauritius reef example, recently we found a great success in preserving coral reefs through technological breeding. They found a new method, a lab coral breeding method, that brings a 98% survival rate in the ocean heat spikes compared to the previous method that yielded about 10%. By directly breeding corals that can adapt to the new heat environment, we can successfully preserve coral reefs while giving us more time to reduce global warming. The second solution is carbon capture. While still in its infancy, the idea is quite simple. We catch back carbon released to the atmosphere and use it again. One specific form of carbon capture that is relevant to the talk will be direct ocean capture, DOC technology. Last year in Hawaii, one of the researcher facilities began to extract CO2 directly from the upper ocean layers by gas extractions and electrodialysis technology, similar to the atmospheric method but specifically engineered for water filtration. By directly mitigating the carbon amount released, we can view a long-term development to slowly scale our efforts to lower water acidification and global temperature, restoring the environment for coral reefs.
Our leverage points are meaningful, but every intervention carries risk. With heat-resistant coral breeding, scientists selectively focus on only the most heat-tolerant individuals. That naturally reduces the number of coral species being reproduced, and that means reproduced biodiversity across the reef, and biodiversity is exactly what gives a reef its long-term resilience. That means reduced biodiversity across the reef, and biodiversity is exactly what gives a reef its long-term resilience. De Filippo et al. Found that even under the best conditions, assisted evolution requires over a century of sustained effort to produce meaningful results. Not just technical limitations, but international regulations itself is very difficult to form into a realistic agreement, let alone showing performance. Education itself too will depend heavily on the national culture and acceptance towards sustainable actions in the first place. Both international regulations and regional education will face barriers.
Nevertheless, we believe our leverage points are long-term, but it's not revolutionary. Education, regulation, and green finance are the most immediately actionable because they can be implemented through institutions that already exist. By contrast, heat-resistant coral breeding and direct ocean carbon capture are promising, but they are still expensive, technically limited, and difficult to scale quickly. So, in our model, the most realistic pathway is layered action. First, reduce emissions, then strengthen regulation and public awareness, and finally, use restoration technologies to protect the reefs that remain. In short, recovery is possible, but only if mitigation, adaptation, and governance move together rather than rely on technology alone. Thank you.
We are ESC!
Yay!
Give us A+.
I was gonna add that.